Welcome back to the classroom. My name is Mr. Wong, joining in our series of Earth and Space. Today's lesson is going to be on about the life cycle of a star. The lesson intention is to outline the life cycle of the star, and our success criteria is to compare the different life cycles of a low mass star and a high mass star. So, just to begin on our journey with the life cycle of stars, we're going to look at all the different stages, and then we're going to also look at how, when stars die, how differently they actually go through that passing on the torch. So, just a quick recap. Stars are made of mostly hydrogen and helium. They are in the plasma state, and our sun is one type of star that has planets orbiting around it, which makes our solar system. So this is a nice little image to show the different stages of each star. You can see that our sun is actually quite small in the grand scheme of things, and it can't create things like a supernova or a black hole. So we're going to look at what the differences are of different star types, and then we'll go into a bit more detail from there. Okay. So another little diagram we can use, we have what we call the main sequence. So this is the stage in which stars are still alive, they're burning up fuel. When they begin to lose fuel, or they run out of fuel to burn, they become what we know as red giants. They could be, or supergiants, which end up becoming supernovas, or planetary nebula. Okay, we'll start with the very beginning of a star's life, and that becomes when they are a nebula. So nebula, as you can actually see here, really incredible images. Obviously, you can't actually visibly see a nebula. They don't actually emit radiation in the visible spectra. Although the diagrams that we show and the animations we show are incredible colors, we actually need to detect it in the infrared or microwave spectra, and then we use the color conversions to make the color contrasts that you see right now. So a nebula is an enormous cloud of dust and gas occupying the space between stars and acting as a nursery for new stars. So this is like the beginning stage that all stars need to start off with. Okay, it's made of mostly hydrogen and ionized gases. Again, like we said before, it's in the plasma state. It's about 1% of the solar mass. So if we compare the mass of a nebula with an actual sun in the main sequence, it's about 1% of that mass. The word nebula derives from the Latin word nebula, which means mist, vapor, fog, smoke, or exhalation. So that's kind of where you see there's sort of like a dust cloud. We have the protostar, which is the second stage of the star's stage. You could say this is the stage where the star is actually beginning to form into what we now see as an actual star, as you can see with the formation in this animation here. So stars begin to form clouds of gas in space. That's our nebula. The cold temperatures and high densities of these clouds begin to increase the gravitational pull towards a specific center point. And then we have what we call a gravitational collapse that begins to form the protostar. Okay, at this stage, to actually develop from protostar to an actual main sequence star takes about 100,000 to maybe 10 million years, depending on the mass the star eventually becomes. The protostar looks like a star, but its core is not hot enough for an actual fusion reaction. What we talk about fusion, nuclear fusion, this is the actual process in which the star generates energy into the universe. So at this stage, the protostar is getting towards it, accumulating more mass, but it's still not hot enough in the core to produce the type of energies that we see in actual stars. Okay. A protostar makes up about 8% of the solar mass. If we actually do the comparisons, protostars that have a mass that's lower than this 8% barrier, their temperatures aren't sufficient enough for hydrogen burning, and hence they actually become brown dwarf stars. So they end up becoming dwarf stars and not an actual main sequence star that we talk about with our sun. We also talked about in terms of detecting protostars and nebula. You can't actually see them very well. You actually need to use infrared or microwave telescopes to detect the different wavelengths that are being emitted. We move on to the main sequence stars. So these are the stars that are still burning fuel, still causing nuclear fusion, to be more correct. And you have our sun, which is nice red yellow, and then you have the more bigger stars, which are more blue and white colors. So the main sequence stars fuse hydrogen atoms to form helium in their core. This is a process known as nuclear fusion. This is where we produce most of the energy and other forms of radiation. About 90% of all stars in our universe, including our sun, is part of the main sequence stars. So if you recall when we showed the Hertzsprung-Russell diagram, the main sequence stars look like so. The actual chart, to quote them together, you can see a number down here from 3,000 to about 30,000. That's the surface temperature of these stars. Our star is about 5,000 to 6,000 Kelvin. You might have never heard of Kelvin before, but Kelvin is just another way of measuring temperature. It's the actual SI units to measure temperature and not degrees Celsius. Here we have a chart known as luminosity, so in terms of the brightness of the star. So you can see the hotter, or at least in the main sequence stars, the higher the temperature, the greater the brightness or luminosity. Our star or our sun is around the K to G stage. So you can see the barrier of 5,000 Kelvin to 5,800. So our star is around this range. This isn't an exact representation of how big the stars are in comparison, but you can see if our sun was around the G state or the G class, there are stars that are much larger than it in this universe. Okay, so we now go into the stage in which stars begin to die. We're going to firstly look at a low mass star, and then we'll look down here for the massive stars. Okay, but before we go into that, I just want to look at the red giants here. So when all stars begin to die, they lose fuel. And so because they don't have enough fuel to push or because they're running out of fuel, okay, that causes an incredible amount of expansion in the star. As a matter of fact, when our sun will die, the predictions for the expansion of the red giant for our sun will be enough to cover the distance from the sun to Mercury, Venus, Earth, and Mars. So in about 5 billion years' time, when our sun does run out of fuel and begins to expand, we actually know that it will actually engulf all 4 of the terrestrial planets. Okay, so let's look at the progress for a low mass star forming a planetary nebula. So a planetary nebula, as you can see in this diagram here, they sort of look like an actual nebula as well, and they kind of appear like planets. So a planetary nebula is an expanding glowing shell of hot gas, plasma, that is cast off towards the end of a low mass star's life. They are named such because early astronomers thought that they looked a bit like planets through a small telescope. After the planet nebula or planetary nebula, these dying stars will form a white dwarf. White dwarfs are what stars like our sun will become when they've exhausted their nuclear fuel. At this stage, the star will expel most of its outer material and forming the white dwarf that we now know. Now, once that dispersing of material, it will cause another gravitational collapse, so it makes the white dwarf very dense. It's actually the second most dense thing in our universe. It's so dense to the point where it tries to clump all the electrons inside that star basically almost side by side to each other. Inside its core, the temperature can exceed 100,000 Kelvin. And as you can see, that's at least 3 times higher than the, let's say, the highest temperature types of stars that we have in the main sequence. Now let's go to the massive stars. So after they become a red supergiant, we get the supernova. Now the supernova is a process where nuclear fuel runs out again, and the core is becomes so heavy that it cannot withstand its own gravitational force, causing it to collapse and causing an explosion of radiation. And this is one of the images that we've taken of a supernova. A fun fact, this supernova is known as SN 1054. Now what 1054 actually stands for is 1054 AD. The reason why it's called that is because this was when we first made records of this supernova, and it was actually made by the Chinese. So Chinese scholars at the time wrote in their quotes or in their journals to have witnessed a supernova event in their country. And so the rumors go, or so the historical records say, that it was so bright that in that particular province where they were looking at the supernova, they experienced 20 days of basically daylight time to just represent how bright the supernova was. There's a real record here. So it was written in this text here. For those who can read Chinese, you might want to have a read of that in the highlighted section there. So that's what we know of with the supernova. At least that's the first time on record, to my understanding, that the supernova was recorded and observed by humans. Supernovas can also form from the collapse of binary star systems. So this isn't so much to do with stars dying, but let's say we have 2 white dwarfs and they cause gravitational attraction towards each other. Okay, one dwarf begins to steal matter from its companion star. Eventually the white dwarf accumulates too much matter and then causing it also to explode into a supernova. So there are 2 ways you can cause supernovas: binary star system collapsing, or, as we're talking about, a high mass star collapsing and dying. Okay, once we get the supernova, once we get this supergiant, we get the black hole. Okay, this is actually the only image. If you look at the internet, there's a lot of interpretations of what black holes look like. This is actually the only actual real image of what a black hole looks like. This image was taken back in, I think, 2019. So it was quite an incredible thing to achieve, and it wasn't done just by one camera. It was done by multiple cameras around the world collating data together. Okay, so a black hole is a place in space where gravity is so strong that even light cannot escape it. Hence why black holes are invisible to us, or we can't see it, because there's no visible light coming out of it for us to actually see. We actually need to use some really incredible equipment to actually do that kind of observation. And the last of it is a neutron star. So once we get the black hole, we can also form neutron stars from supernovas. You can see this collapsing here. So a neutron star comes from the collapse of, the supernovas. So it also occurs when the massive star runs out of fuel. The very central region of the star, or the core, collapses, crushing together every proton and electron into a neutron. Now, out of all the things we know in the universe, a neutron star is probably one of the most densely packed material or if not the most densely packed material that we know of. So that's just how dense it is. All the protons and electrons don't have free space. You put them together, clamp them together, and you make the neutron. Hence why we call it a neutron star. All right, so that concludes our lesson. Before we just go off, I just want to show you the periodic table. So the periodic table shows you all the different elements of our universe, and if you actually have a look at it, a lot of these are caused from the dying stages of an actual star. So we have all those in the green and the yellows, dying low mass stars. So you see some of these wouldn't be created unless a low mass star was to die. Explosion of massive stars, so you can see those here. We also have merging of neutron stars to create these elements. And we also have these where exploding white dwarfs. So what this shows to you is a lot of the elements of the periodic table would not be able to be formed unless stars have already come and gone. So what that would actually tell us is our solar system is not a first generation star, or our sun is not a first generation star. It's actually at least several generations down the line. And that's the end of my point here. Thank you for joining me on another lesson about Earth and space. I'll see you next time. Take care.